when I'm not carrying flags around, I'm a software engineer at the Havok navigation team. And let's dive into it, and everything will make sense. Today will be time traveling across platforms. And you think, oh, these are the ramblings of a madman? Yes, but everything will make sense. So what we'll do is we'll talk about time travel, about why determinism is kind of interesting for time travel, how to get it, how to test it, and then we'll wrap it up. So let's dive in. Game developers are world creators, and they're creating worlds from the islands of Animal Crossings to the galaxy of Helldivers to the depths of hell in Doom. And Havok is helping game developers realizing their vision since 25 years. That's a quarter of a century with our 3 products, Havok Physics, Havok Cloth, and I'm working on a Havok navigation solution. And these game universes, these intricate simulations, they provide a lot of entertainment to people, and everything is dandy. Someone is playing NetHack, someone is playing Doom, people are playing together here in the middle, and we simulate worlds and pretend that, for example, for the networked game, it's the same world, but actually it's 2 worlds running on 2 computers, and you need to make sure that everything is synced. And everything is cool, everyone is having a lot of fun, until things go wrong. And things will go wrong, and they do go wrong, and then someone needs to step in and debug the problem. Yeah, and this is my guilty pleasure. I really love debugging, so I need to make sure that I'm not allowed to debug just the hardest things, because maybe sometimes it's not that important, but it's really fun to be a detective. And here there is basically one of the foundational examples of why Havok invested a lot in our tooling to find non-determinism. This happens 2015, and Havok engineers had to be helicoptered in on-site to a customer to find out why sometimes this value here we print down there would be 42 instead of 23 on some other computers they would be connected to. And it's a simple example. We call a function which returns which just computes if A is bigger than B, sets a value to 42 if it's bigger, and then just returns this in the argument. And sometimes, as I said, this would diverge, and people really were puzzled why this happens, and we developed tools specifically to hunt down issues like this. This was a networked game. This is not supposed to happen, because you should have the same values on the same thing. So yeah, why would that happen? And so now it's a pop quiz. Write down or remember the answer you're giving. Is this programmer error? Is it undefined behavior? Is it a compiler bug? Or is it D, the mystery option? Write it down or just remember your selection, and onwards we go. So the process of which turns game developers from world creators into bug hunters, what do we actually do? What's the process? And that's a bit of a stylized one. So on the left side, we have what we heard about. So we hear that things are crashing, and the dotted lines means, yeah, okay, we know something went wrong. We have the crash dumps, the little skulls. We can investigate the crash dumps. Sometimes we have the heap, sometimes we don't. And we have the last cries of help, which is the call stack, and can investigate some things on the call stack. And we now have a murder mystery where sometimes we turn out to be the murderer as well. And now we try to reproduce all of this. What happened? Like, the guy is lying dead on the floor, or so we heard in the bug reports and the JIRA tickets. And we try to reproduce the issue live over and over again. We put some log messages in. It's like here, printf debugging, trace points, things like that. Breakpoints, why is this happening? And sometimes we're able to reproduce it. And we have the call stack. What you don't know what really happened, because the state has been lost. It's basically the egg has been scrambled. We can't unscramble the egg. We can, from some of our log messages, use that something happened. And now here, we're on the yellow arrow. We now have a really good theory what will happen, and we are about to diverge into a function which then will crash. And we are like, okay, deep breath, let's get a coffee. Let's find our best programmer friend, get him back, and then we'll debug the thing. So off we go, get the coffee, and come back to our machine. And we're like, that's nice. Now we're safe. safe security updates have been applied, but now we have to go and reproduce the issue over and over again. So on the right side, wouldn't it be nice if we would have the basically crashed process? Wouldn't it be nice if in this fantasy we could time travel? So the egg has been scrambled, but now let's slowly rewind time. It's like a sports cam. There has been like an accident. It's like, oh, let's watch this again. Go back and see when it went wrong and slow replay forward. We missed it, rewind back, place breakpoints and hit them backwards, and memory breakpoints, hit them backwards. And that would be really, really nice. It's a fantasy, yeah, but it also exists, and it's called time travel debugging, yeah. And so someone went and built a time machine out of a debugger, yeah. And this is WinDebug, yeah. It's the more complicated, in quotes, debugger Windows has. It's not the built-in Visual Studio one. It's not in Visual Studio yet, but this is live. You can get it now. It is released since late last year. Give it a go. It's amazing what it can do. You start your program under the debugger. You start it, record the trace. Everything is nice. And then once you have a crashed program, you can actually go and set a breakpoint and hit it backwards. So you can rewind to the start of your recording, and you can step every single step of the program, every function call. You can step in, you can step out, you can step over, you can do all of that. Hit breakpoints backwards in time, hit memory breakpoints backwards in time, go forward, investigate as much as you want, see the egg being scrambled. It's like, oh, here it went wrong, and fix the bug. This is amazing. Why is no one using that? Or not that many people. So it's a surprise often to people that this exists. So this is the instant replay for all of this. Infinite resolution tracing, backwards, forwards, memory breakpoints, deterministic post-mortem debugging. The process is not live anymore. We have a recording. So we can hand it around. We can give it to our friends. Why is no one using this? Well, there are multiple issues with it. First of all, the platforms you can use it on. On Linux, this is RR, the replay and record and replay debugger. It's also really useful, but it's slow down. So if you have a 60 FPS game, most likely you get 3 or so, which is unplayable in a lot of instances. The traces are gigantic. This is a trace, 10 seconds in our demo framework, which doesn't do that much. And you still need to reproduce the issue. So if you have a Heisenberg and you need to reproduce and it takes like 3 times to repro, well, okay, lucky if you have the tracing on. If you don't have the tracing on, well, it's lost. So that's not good. But determinism to the rescue. Yeah. So determinism. Have I ever told you the definition of determinism? Well, determinism is doing the exact same thing over and over again, expecting the same outcome. This is the definition of determinism. Yeah. So determinism is the absence of choice, if you're really, really philosophical. Yeah. So that means the same inputs give the same outputs. But if we do cross-platform determinism, if we want to have the same AI behaviors on one machine than on the other, and they have different platforms, we allow different paths to be taken because we know that the ARM processor does different things than an x64 processor. But the outputs need to be the same. The ones we care about, they need to be the same. If there's a choice and one of the platforms chooses a different choice than all of the others, this is not deterministic, and that's basically non-determinism. So determinism is not correctness. Deterministically wrong is still deterministic. Otherwise, we couldn't repro a bug or anything like this. It would be random. Yeah, it's not correctness. We only care about the results. And determinism is result comparison. If we know an expected result, yeah, we can verify that this result happened. So we can hash the world state, and we can then, if we rerun it and we expect the system to be deterministic, it should be the same. Yeah? And so we can store hashes of world states for, I don't know, 1,000 characters doing collision avoidance, and it should be the same if we rerun it again. And we can do that on CI and say, you broke determinism on this test because now the RBO doesn't work anymore. And we use that to check for unintended consequences. So unintended changes. I just updated the vector library. Why do I have these bugs assigned to me? Yeah, you broke everything. So you can hash states. And with that, you also realize that it's compression. Determinism is compression. If the input is enough to reproduce all of the intermediate steps and the output, you can just give me the start state, the inputs, and I'll arrive at the outputs if I rerun the thing. And with this, we can just rerun from scratch. And it's a little bit that's really the power where it's in, because that means this enables snapshot replays. We can have a small recorder running and collecting snapshots. And then we can tell the customer, well, you see weird behavior, just put on our small recorder and send us over, and we are able to reproduce their issues. And if it's cross-platform deterministic, we can take their weird navigation behavior from their ARM processor and reproduce it in x64 really debug. We can step, see everything. We don't need to de-optimize or anything like that. We can go to the frame and find the issues. So we can freeze the snapshots and we can defrost them on our side. And that's really powerful because this is time travel. Yeah, because we can do it over and over and over again and find the issue and just step through. But it's not as expensive because our system is deterministic. And so snapshot and debugger is time travel debugging. So now we know why people would like to be deterministic, because you can time travel and you can time travel across platforms. And that's really nice because it's basically going back and you can do whatever you want with this trace, and customers can give you this. And so we achieved it. We can basically time travel between platforms. It's extremely powerful. And yeah, we heavily rely on this at Havok for our physics product, for the cloth, and for the navigation thing. And it only works if the system is cross-platform deterministic. So we need cross-platform determinism. This is what Havok is doing. These are our 3 products, and we have some helper things around it as well. We have a lot of stuff. We have a lot of features, and we have a lot of complexity. And we do all of these features and this complexity on some platforms. And we do that on some platforms, on some compilers, and some build configs. And we need to be deterministic across all of these in order to reap the benefits, to really reap the benefits. So we want reliable reproduction with customer snapshots. We want to prevent regressions. So if someone broke the collision avoidance, we want to know about it. And we want to reduce our pain because we had to shut Havok down twice a year to make our releases because people had to manually verify that behaviors are still happening as they were supposed to. We had 27 of these. So basically it was a lottery going on who got the worst platform, where they have to go and check all the demos and see if it worked. Now we don't have to, because we just check. If on one platform it works, we do that manually. And by having the hashes on all of the other platforms, we know they behave the same. So it's incredibly powerful. Cross-platform determinism solves everything for us. I mean, at least, so I claim. So now we need to go and build the time machine. And again, what do we want? Well, we want to do the exact same thing over and over again on all of the platforms. Which sounds easy, but is quite hard, because we have the source code, we transform it with a compiler into binary, it runs on some silicon, and all of these things have little bits which can make things non-deterministic. You have some choice points yourself, which is, oh, you write the code, you write some compiler flags, you set some CPU flags. But some of these things are out of your control. Like someone makes a new chip, people want to run games on it. Well, now you're on the hook to maybe make it deterministic on that. So we have our source code, we have all of these compiler settings, we transform this stuff into binaries, and it then runs on different real machines. And it goes and it takes input and it generates output. And we expect the outputs to be the same if the inputs are the same. This is what we need to achieve. And there are some causes, I think it's almost all of them, which can cause non-determinism in your code, in your game, which is non-deterministic input. Yeah, I mean, it's kind of, some of these are very, very obvious, but we'll see that it's a little bit more insidious. There can be hidden inputs you didn't think about. Operations can be swapped around, and that can make a difference. Let's say shoot gun or pull trigger load gun is different from load gun pull trigger. Yeah, and so if operations are completely different, well, what did we expect? We're not deterministic. But sometimes the compiler might do that for you. So we need to take a look. And all of these causes can hide in any of the things on the right side, which is your systems, your source code, your programming language, your runtime system, your computations with floating points, or on the silicon itself. So these are the things sometimes you don't control. And so non-determinism is everywhere. We want to have cross-platform determinism. Let's have an easy test how to find non-determinism in your systems. Well, are there any choices you don't control? Yes. If two systems, which are different, they still have a choice, and they make the choice, and not you, then they might do different choices. And if the systems make different choices, well, then you're non-deterministic, and it's not in your control. So you need to eliminate these choices from these systems so that they can't make bad choices. It's a little bit like parenting. I'm not a father. I make a lot of bad jokes, but I imagine it's like that. There's a quote about motion matching. It's a little bit like parenting. You'd like to set them up for good choices, and then you let them go and see what's happening. And let's take the first one, which was, non-deterministic inputs. And that's a little bit of a bummer because frame times are not deterministic, so you need to completely decouple your system from frame times. Your simulation times need to be fixed, and then you have a hope at achieving determinism. And don't use true random number generators. Don't access local time or the file system or anything like this if you want to be deterministic. What it also means that these are the points where the systems can disagree, where one computer might have a different frame time than another one, and obviously then you'll diverge, or it rolls a different dice, or the time is locally different. So don't do it, yes. Don't have different inputs. Some of the advices will be, do people know the draw an owl, where it's two circles? It's like how to draw an owl, and then it's two circles, and then draw the rest of the owl, yeah? So pat down all of your inputs, and don't do non-deterministic inputs, is the advice here. Here, another example about hidden inputs. I wrote something like this, Young Richard, in 2014. It's basically just reading from command line, not hard-coded. It reads some values for width and height of an image, and you want to scale the image. And it was for Hitman 2016. I was working on it in the pipeline, just image scaling of Hitman outfits, items, things like this. And it worked perfectly. Really nice, dirty code. Don't do that, but, well, it worked. Until it didn't, yeah? There were reports that there were corrupted images, crashes on build servers, what's going on. And also, funnily, it was only one build server. One build server in Copenhagen, and that's one of the hints, crashed the thing. What's going on? And also, the second line here is what it got as the input. It was like 1024.77 times tiny number. What's going on? So the answer is, this build server had Danish as the locale. And the Danish locale says that the comma is the period point. And so it reads the first thing in as a double. That's perfectly fine. Then we don't have anything left, so we actually don't initialize double. We read an uninitialized memory. Well, that's not great. So you have a hidden input in the state of the system. Don't do that, yeah? Don't have hidden input, but it's also really hard to find. So don't just assume that all input is known. You actually need to pat it down and need to make sure that you don't have input hidden somewhere. Be on the lookout. So what we need to do as well is we need to rein in multi-threading. So that's an order issue usually. Havok does deterministic task graphs. So systems have task graphs which are completely deterministic. They are basically written in code. And then to the right, this B task might be embarrassingly parallel, which I almost can't pronounce. But it's basically no dependencies between the tasks. You can't just go and do as many of them as you want. And with this, with the task graphs and the dependencies, if you model them properly, you are deterministic. You basically wait until the things are done and you do them in the right order. Where multithreading will trip you up, if you do the embarrassingly parallel thing and you have a worker thread working on this, I mean, one worker is not that complicated. But if You do it slightly differently, for example, different input order, because someone called an API in a different way, like adding characters to the world, AI characters in a different order. Well, you get different outputs for different inputs. Yeah, okay, quite obvious. But that's not good, because in theory, if then, let's say, a tie break is happening based on position in an array or something like this, you will get different outcomes. A character will go left instead of right, and then two systems will disagree on what to do. So sort your inputs or make sure that things are in a consistent order when you hand them in. And then we need to make sure that they come out on the other end in a consistent order as well. And that's also quite hard, because what if we add a second worker because we want multi-threading, and now the worker 2 takes off packages from the queue and they come out in a different order, because first we finish B, then C, then A, then D, and that's different than the first order. What if we move it around, because scheduling did not allow us to run different order? All of these, the systems we just saw, they disagree about the outputs. That's not good. These are disagreements you don't control, and so that's non-deterministic. What you need to do in the end, you need to sort the outputs if your outputs are relevant. The sortedness, that's a word, is relevant to your determinism. You can also emit packages in a known order. So if you know A, where it needs to go in memory, just do that. You don't need to sort, because sorting can be expensive. But sometimes tasks are productive and they produce A to 1 to n different results. So maybe you need to resort to sorting. And so don't just assume that multi-threading is a great way to make things go fast. It's also a great way to make things go wrong. And so you might need to sort your outputs or emit them into slots. And you need to have a fixed task graph, or at least that's what we do. There are multiple ways to do it, but that's something which works for us. The task graph for Havok physics is gigantic. Yeah, so it's quite nice. We have a DGML output where you see the graph and you're investigating. It's quite something to look at. And it didn't fit on the slide. So ensure the same input order, and off we go to our most favorite, one of our most favorite topics is our programming language we're using, which is C++ in our case. And it has a lot of behaviors. And some of them are implementation-defined behaviors. So for example, standard rand, that's a thing. Then it has unspecified behavior, which is, for example, the argument order evaluation. So for function f, and you call it with next int. And then there's undefined behavior. The thing is, everyone has heard undefined behavior is evil, which it is, so don't do it. But the other two don't sound that bad. Well, one of them, for example, implementation-defined behavior, it's up to the implementation. Unspecified behavior, the compiler has multiple options to choose from, and they don't even need to tell you which one they chose, because they can choose dynamically. All of that doesn't sound that great, yeah? Because all of these are disagreements between different compilers which could do different things, or the same compiler with different settings could disagree with itself in the different setting. So all of these are danger zones. Mine's going off, non-determinism everywhere. So don't do undefined behavior, yes, but also rein in implementation-defined behavior. Don't use std-rand, they have better options by now. But also know you have a list from your compiler maker which things are implementation-defined, and the outcomes, if they influence your outcomes of your simulation or your AI, you need to make sure that it's the same choice. And if it's not the same choice, you need to re-implement it yourself in a deterministic way. If that's in library code, so we are a library, and people might call us with some functions. We need to check certain assumptions. And it's really important to have automation to weed out things. And for example, use ubsand, cpp check, and other things. We didn't have that much luck with any of these tools. So far, our other tooling is way better at catching non-determinism. I'll show it in a minute. So we talked about multi-threading. We talked about C++. Now let's talk about the most favorite topic of everyone, IEEE 754. Or how I call it, the number of the beast. Yeah? Because I also think IEEE is the sound some people make when they think about floating point numbers. me including. It's like, yeah, you know, I've seen this image. Yeah, yeah, there is stuff going on. We have a sign and we shift around the binary point. All of that is great. So let's go back to our foundational example. And the foundational example is we have sometimes 42 on some platforms and 23 on the other side. What's going on? And there's the hint as well. This was on x86 in release mode. It said 42, and otherwise it said 23. And this is, I mean, a bit of a nerdy thing. So it's basically float A is handed in as a reference, and the compiler is very, very, very helpful. It's like, oh, that's a reference. I hand it in a register. And x86 has a special mode for registers, which is extended precision mode. It's very helpful because it knows that you want to have 80-bit precision instead of 32-bit. And this is only happening in release mode. And the compiler decides, oh, I know this is a reference. I'm an optimizing compiler. Let's put it into this register. So this is the disagreement you can't control. And the only way to know that this is happening is to take a look at the assembly code. And knowing that the FPU on x86 has this weirdness with the 80-bit precision. So yeah, it actually did something different. It's not the same. Your operations were different. So that's where the non-determinism came from. And this is a visualization of what happened. Is on the top you have a floating point with lower precision. On the bottom you have floating point with a higher precision. There are some numbers. You hit them, and one rounds down, the other one rounds up, or rounds to a different value. And then A is bigger than B, and you go the wrong way. So rounding, precision and rounding are the things which will trip you up in IEEE 754. Luckily, we have it. Otherwise, it would be completely unspecified. So these were the rounding modes. They're not that important. There's a flag for it. But I claim that lots or all of floating point computations differences are caused by rounding and precision. It was way worse in former times. So x86 is around, but we don't support cross-platform determinism. Now is the amazing, blessed time of cross-platform determinism, because all of the 64-bit platforms, they agree on IEEE 754 precisions, because then they can't disagree. All major platforms currently do that. So let's ask the standard who they were thinking about cross-platform determinism. They're very helpful. It should be possible. Yeah, they don't tell you how, they don't tell you steps. They are optimistic. There is in the 2008 standard, I think, 1.5 pages at the very end, page 11. The whole standard is around like 80 pages. So actually it's kind of readable. It's standardese, but yeah, you get it. So what's in the standard? The standard defines, we saw our binary formats, the main ones, float and double, so 32 binary and 64 binary. But it also gives us basic operations, comparisons, float conversions, and rounding modes. And if you take a look, if rounding disagrees, we saw that's not good. And there's a flag in your processor at runtime which can decide which way to round. Some libraries might set this, and there are hilarious bugs where someone links a library to his program and suddenly everything is wrong. And this is because it set the rounding mode or precision. Don't do that. Check. So what we do is we start our threads with the right setting, and we can do spot checks in the dev builds that no one fudged with it. Yeah, because otherwise we go wrong, and that's not great because it's really hard to find. Then there's another flag. This is a very, very trivial question. There are very tiny numbers called denormals which behave differently. So everyone usually switches them off because behaving differently is a special case which is slow. So you put this flag and you flush all of the tiny numbers to 0. They're really, really tiny, used for scientific computation. And there could be a disagreement, though, in how this flushing happens. So you need to take care if you use this flag. And there is also from the ARM developer page, I don't know if you can read it, but it says this is strictly a violation of IEEE 754, which doesn't sound that great. So be very careful with these flags, and you need to know what you're doing. A reminder, because of all of this rounding, floating point math is not associative. You can't just go around and say, oh, well, a plus b plus c, well, I'll bracket it like this, a plus b plus c doesn't really equal a plus b plus c. Because what it's doing under the hood, it's doing 2 rounds, either rounds first a plus b and then adds c and rounds it again, or it first rounds b plus c, adds a, and then rounds it. There is destructive inference going on there. So if you add a small number to a large number, the small number is gone. It's hidden in the precision, and it's gone. And it makes a big difference if you do, let's say, a plus minus a plus a small number or something like that. So you really need to think. And the funny thing is, the optimizer, if the optimizer would do reassociation because it's smart and trying to factor out some terms and then it doesn't have to redo them, well, then things go wrong because these are disagreements of 2 different systems if a compiler can decide. And the funny thing about all of this is that this is also happening with fused multiply add, where you have a times b plus c. And you don't want to round twice, so let's just round once. That's faster, isn't it? And this is also wrong or non-deterministic. And what I want to say is, the fun thing is, this is called fast math, which I call wrong math. So, because the definition is, it relaxes IEEE strict rules. And actually, it violates IEEE's strict rules. And the compilers then do smart things. It might give you some cycles, but it's also causing disagreements across all your nicely deterministic systems. So because it's actually doing different operations. And these are hidden inside of your compiler. So you need to prevent your compiler doing all of these things by not, first of all, targeting x86 if you want to do cross-platform determinism, because it's a gigantic pain to wrestle with the x87 FPU and the 80-bit precision stuff. Don't use fast math. Yeah, it's a trap. And don't allow fused multiply add. You have some compiler options there as well. You can use fused multiply add specifically, like explicitly yourself. It is IEEE standardized by now. But just don't let the compiler decide, oh, I want to use it here and not there, and then in a different mode or optimization level, choose differently. And be wary about the flushing of the normals. So again, the guarantees. Does someone notice something? What's not in there? Well, just some trigonometric functions, some exponentials and log functions, some math constants. Who needs them anyway? Well, that's not good. That's not good, because that also means you can't use standard math libraries. You are not, because none of these sinus, cosinus, and all of these things are defined how they are implemented specifically. So it can be quite different across implementations. So this is a disagreement, and now we go back to our owl. So all you have to do is you have to write your own deterministic math library, and it needs to do the same thing across all of the platforms. Yeah, I didn't do it. The Havok math implementers did do it. So I benefit tremendously because I sit on top and I don't need to think about any of these things. This is what you have to do, or you have to find someone who wrote such a library. It might be fine if you're on one limited set of platforms, then maybe you can get away with using the standard platform if you use one compiler. So you need to know that this is a gigantic trap. Here is a list of stuff you need to do. It will be all in the slides. So again, no fast math, strict mode. Use x64 or similar because they agree on all of the math on the precision. Don't allow your compiler to fudge with your things, so no fused multiply add automatically. Control all of the hidden flags, and just, minor note, implement your own math library. IEEE over. What else can cause non-determinism? Well, this is the Intel Pentium bug. Does someone know what I'm referring to? There was a bug, the so-called fdiv bug, that this chip didn't math correctly. Sometimes, for some specific values, it gave you the wrong answers. It wouldn't have mattered, even if not, I think it was a scientist found it. It was like, what's that? And then Intel had to recall the whole thing. Even, I think, Romero said they ran into this bug and were seeing through walls on specific angles sometimes on this chip. Luckily, this is in the past. and it doesn't happen that often anymore. Yeah, except when it happens again with the 13th and 14th generation Intel processors. And some people then get bug reports. We just had issues with Git on some computers where it would crash. Oodle, which is a texture compression thing, which is also used in Unreal, they got bug reports, and they usually don't interact with end customers. And it was like, yeah, well, it doesn't math. And also, Mozilla engineers know that how hot it is in Europe based on what's the locale of the crashing systems on Intel 13th and 14th generation. So this can also still break you. So you need the control of the input, all of your task scheduling, all of this. Congratulations, you're deterministic for now, because any changes might undo your work. So now what we need is we need to stay deterministic. So come with me if you want to be deterministic. I'm Austrian, so that's fine. So any changes can lead to non-determinism. And we use the determinism checker util to make sure of that. And it has two modes, succinct mode, basic mode, and bug hunting, non-determinism hunting mode. So let's take a look at that. We can run all of our things with snapshotting enabled, and it's snapshotting with a world state, and then all of the commands are recording the input and the output. And that's what the blue thing is on the right side. We hash all of the stuff, and we check if the hashes are equal. If the hashes are not equal, someone needs to go and take a look at this log. And the log looks like this. It's JSON. You see the frame. Oh, on frame 7, there was a non-determinism desync. You also see what the operation IDs were and what the inputs to the operations were, the operation data. And then you can go look up the operation ID in source code and make up your theory and find the desync. And this is nice, but also it's sometimes only a good first start. Sometimes you don't see what's going on because it's happening on, let's say, ARM device or something like that, and you can't find it in debug. So what we then need to do is we need to do more time travel, and we need to do something like this, which is a leader PC has more binary traces, way more traces, more of these little commands. We instrument more of them. We take this trace and send it back in time to then have the determinator next to the runs, and it checks, hey, your output of this function, is it what I recorded before? And if not, it shoots it in the head. Yeah, and shooting in the head is having a debug break, and you can basically, you have your debugger attached. You can attach your debugger. You see the source code, and you see what's going wrong. And you see what's the current result, what's the expected result. You see the stack trace. And basically, this is a really good point to find non-deterministic input or computation on device in your debugger. All of that is nice. And we are actually able to find a lot of issues with this. Staying deterministic is an ongoing struggle. There are always new sources, new exciting sources of non-determinism. And it needs continuous testing, which we do with our determinism checker util. So let's wrap it up. We're out of time. So first of all, other uses of non-determinism. It's not just that we really like it to verify our AI behavior, navigation meshes, collision avoidance, things like this. It's also used for replays, for example, Doom, CSGO, things like that. Network replication is a really big topic. And for strategy games, you only want to send small commands, and you don't want to send the movement of 1,000 or more characters around. That's called deterministic lockstep. You also have deterministic rollback, where you speculative execute into the future, but then you need to be able to roll back and do something new. And we want to have stable build artifacts where the nav meshes should be the same. All of our nav links should be the same from build over build if the inputs are the same. That's where a little bit of the sorting comes in as well. Well, determinism is the absence of choice. You need to exclude all of the disagreements in choices you don't make of the systems they could make themselves. And these choices could come from inputs, task scheduling, programming language, floating point numbers, all of these things. Just write your own math library, your own task system as well. Eliminate all of these disagreements, and you reap the benefits. And so our investments in our math library, in our deterministic task system and testing the determinism check util and the determinator. Unlocked full cross-platform determinism on 64-bit platforms. For physics and navigation, we go for full determinism. PC, x64, Intel, AMD, Xbox, PlayStation, ARM64, Switch. For cloth, we soften it a little bit because we really, really like fast inverse square root. So we have islands of determinism. So ARM is its own thing, and x64 is its own thing. So these are the guarantees. We still get good snapshotting and all of the benefits there. We reduced our manual testing from 27 to 1 configuration, which is amazing because everyone hated it. And snapshot debugging is, I think, one of the tools people can take away here as well. Well, also try out WinDebug. It exists. It's really cool, especially if you combine it with snapshotting. You can run it under time travel debugger and actually then do time travel while you do the snapshot debugging. So we're doing a little bit of inception there. I showed, you now know how to identify and combat common sources of non-determinism, how to build and test for non-determinism, and how to debug across platforms and time. At Havok, this is priceless. I hope it can be for you as well. Happy time travel across platforms. Thank you for your attention and any questions.